Welcome students. So today we want to discuss about solving a differential equation using variation of parameters. So recall, what did we do in the last class? We had y double prime plus a times y prime plus b times y equals to some g of t. We solved this second order differential equation with constant coefficients. And we had g of t was of special form. It was either a polynomial, it was either an exponential, or sine or cosine, or sum or product of these. Now we want to move to the next step. What if this g of t is not a multiple, is neither of this? That means it's not a polynomial, exponential, sine or cosine, or their products. So how would we go about it? So for that, we have variation of parameter. So again, let's start with a non-homogeneous differential equation. Again, we are interested in second order. So you see y double prime, that indicates a second order. The coefficient, so it's a linear differential equation because you see the coefficient of y and y prime and y double prime are functions of t. And it's non-homogeneous because we are assuming that there's g of t on this side, which may not be zero. So now we want to basically find the particular solution to this differential equation. Okay. So suppose we are given y1 and y2 are fundamental set of the homogeneous differential equation. That means you set g of x equals to g of t equals to 0, and you get the corresponding homogeneous differential equation. So that means what? That means the complementary solution yc. What was the complementary solution? Complementary solution was a solution to the homogeneous differential equation you get out of setting g of t equals to 0. Yeah. So we got complementary solution was c1 y1 of t plus c2 y2 of t. And now we want to find out what? We want to find out a yp, which is a particular solution. Yeah. Now note that we are given y1, y2 are the fundamental set of solution. We can do this easily. We can find y1 and y2 if the coefficients are constant. Coefficients, that means p of t and q of t are constant. Yeah, then we can find out if this p of t here and q of t is constant, we can find out the solution to the homogeneous differential equation using the characteristic equation. Otherwise we need more techniques, and hopefully we will see how to use power series to see the solution. So right now the premise is you are having this second order differential equation, non-homogeneous, and you are given the fundamental set of solution. So let's see how do we basically find out yp. Okay. So in this case, we'll postulate that yp is of special form. So again, postulate that yp is of form yp of t is same as u1t of y1 plus u2t of y2. And then the goal is find u1 and u2. Yeah, note that these are not constants. Okay, these are functions. So let's see how and what u1 and u2 will be, or if there is such a possibility for u1 and u2. So substitute So we'll substitute y equals to yp t, which is same as u1 y1 plus u2 y2 into your given differential equation y double prime plus p y prime plus qy equals to g. Yeah, note that these y, p, q, and g are functions, okay? So now we want to substitute them in this differential equation, so we need to find out the derivatives. So let's see. So what is y prime? Y prime, you have to use product rule in both of these. So product rule here will give me u1 prime y1 plus u1 y1 prime, and using the product rule in this part, we'll get u2 prime y2 plus u2 y2 prime. Okay, and now if you rearrange this is slightly arrangement will go as follows. So you get u1 prime y1 plus u2 prime y2. I'm going to rearrange a little bit, plus u1 y1 prime plus u2 y2 prime. Now see, you have y equals to u1 y1 plus u2 y2, where u1 and u2 are variables. So we want to basically find u1 and u2, which will help us do the computation. So for example, suppose you're given x plus y equals to 4. Then there are many choices of x, and correspondingly you get choices for y. So we'll choose in this case. So choose, we want to find out u1 and u2 which works. So choose u1 and u2 in a way such that, or in a way, we get what? We get u1 y1 plus u2 2 equals to 0. Okay, so that will leave us, that will imply y1 equals to u1. So I'm basically equating this guy to 0. And again, why am I doing that? Because I want to be able to compute something. Otherwise, as you can see in this case, you have x plus y equals to 4. You want to solve it, then you restrict your x to be, say, 0, then you get y equals to 4. So same way, I'm going to do a restriction here so that I can solve it. Otherwise, there are infinitely many solutions to this. So let's work this out. So I get y1 prime, then, so I'm setting this to get 0. So that means y1 prime will be same as this guy here. So what do we get? We get u1 y1. So u1, so we get what? We set u1 y1 prime plus u2 y2 prime. Now, again, we want to basically put this in the original differential equation here. So we need to find the second derivative of this. So let's find the second derivative of this. So y double prime, again, we have to use the product rule on each one of them. We have u1 prime y1 prime plus u1 y1 double prime. Same thing here, u2 prime y2 prime plus u2 y2 double prime. So this is what you got, and then substitute 1 and 2. So let's substitute everything in star. So substitute 1 and 2 in equation, original differential equation star. You will get y double prime plus p of py prime plus qy equals to g becomes, so what does this becomes? This becomes, let's write it here. So u1 prime y1 prime u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. That was just the first part, plus p times u1 y1 prime plus u2 y2 prime. That was the second part, py prime, plus qy, which is q times u1 y1 plus u2 y2, and that is equal to g. Now notice we can, so now it's time to rearrange and cancel off terms. So notice the following terms. So you have this term here, so u1 y1 double prime. So take this term, and then again u1, you need this term here, and then take this term together and see what do you get. So let's arrange them together. So this implies u1 y1 double prime plus p y1 prime plus q y1. That is the first part. Similarly, we can organize these terms together as well. So which terms? So we'll take the one with this term, and this term together. So what do we get in that case? We get u2 times y2 double prime plus p y2 prime plus q y1 plus, what is left out now? We are left out with u1 y1 prime. We are left out with this guy. So we get u1 y1 prime plus u2 y2 prime, and that is equal to g. So now note that y1 and y2, what are y1 and y2? y1 and y2 are solution, the fundamental set of the solution to the homogeneous part, right? So that means they will become 0. So what do we get? In this case, this is equal to 0. This is equal to 0. So what do we get from there? We get, this implies u1 y1 prime plus, there's a prime missing from here, u2 prime y2 prime equals to g. So that is an equation. Let's call this, let's give it some number, say equation 3. And if you write down equation 1, sorry, not equation 1, let's call this as equation. So we have what? We have, let's give it a name, equation 0. So from 0 and 3, we get what? This gives us, this gives, let me rewrite again the 0 equation here. So the second equation, so first equation is, let me just write down that here directly. And 0 is, I have, what was my 0th equation? My 0th equation was u1 prime y1 plus u2 prime y2 equals to 0. All right. So now here you have the following. We have now a equation. We have two equations. So two equations and two unknowns. So what are our unknowns? Our unknowns are u1 prime and u2 prime. So let's write this in the matrix form. So in matrix form, what do we get? We get y1, y1 prime. So I'm reading the first equation. So if I read the first equation, I can write it as so y1 prime. So I'll write this as the first equation. So y1 prime, then y2. Then the next equation, y1 prime, and then y2 prime. So this multiplied by u1 prime, u2 prime is going to be 0g. Yeah. Now note that this guy, the determinant of this is what? This is Wronskian. So determinant of, note determinant of y1, y2, y1 prime, y2 prime is equal to Wronskian of 1. So recall, now we can use what? We can use so we want to solve for u1 and u2. So we will use Cramer's rule. So by Cramer's rule, you will get u1 prime is equal to, so by Cramer's rule you will get, so how do you find out the solution? You basically say 0g, you look at determinant of this, then you replace the first. So if you're finding u1 prime, solving for u1 prime, you replace the first one by the following column. So you get first column replaced by this. So you get 0g y2 prime divided by determinant of y1, y2, y1 prime, y2 prime. Yeah, this is what the Cramer's rule is. So what do we get here? We get u1 prime equals to, what is the determinant of this? Minus gy2. And then here we get, this is going to be Wronskian of y1 and y2. And this is non-zero. Why? Because since y1 and y2 are fundamental, right? Since y1, y2 are fundamental. You see that it's important that they be fundamental, otherwise that will be zero. So you got u1 to be this, and similar investigation will show you that your u2 prime is going to be y1 g1 divided by Wronskian of y1 y2. Of course, and note all these are functions of t. Okay. So this leads us to, so now if we integrate, you will get u1 of t is going to be integral of minus g of t. So we can write it as g of s, y2 of s, Wronskian of y1 and y2 of s ds, and then once you integrate, you substitute t in there. And similarly, you will get u2t to be integral, because this is a derivative, right? This is a prime. So therefore, we get u2t is y1 y1 of s g1 of s divided by Wronskian of y1 y2 at s ds, and then after integral you put t inside. So this is your variation of parameter. Okay. Now you may say, well, why did you choose u1 and u2 in a way that they became zero, right? We chose it so that we could solve this equation, get system of equation and solve it. All right. Then question, can we have chosen something else for u1 and u2? Well, perhaps you could have, yeah, but yeah, and that would have worked as well, but we are choosing something which helps us solve this. Okay, so this is the summary of what we discussed now. So if y1, y2 are fundamental set of the solution to this homogeneous differential equation, then the particular solution for this non-homogeneous differential equation is given by y double prime plus p of ty prime plus q of ty. Gt is given by yp u1 t y1 plus u2 t y2. And what is your u1 and u2? U1 and u2 are these functions. So you see, this result is called variation of parameters because you are adjusting u1 and u2 in a way that you get the solution, particular solution. Again, so let's solve the following differential equation now. So y double prime plus y equals to tan t, where t is between 0 and pi by 2. So of course, this part is differential equation, second order with a constant coefficient. But note that we couldn't use variation of parameter because you don't have a polynomial here, neither you have exponential. This is not multiple of sine or cosine, right? So that's why we couldn't use that, right? So let's first solve the following differential equation. So we want to solve the whole thing. So before we find out a general solution, so note that general solution is of form what? Y equals to complementary solution plus any particular solution. It doesn't matter which particular solution you take. So question is, how first we need to find out YC, which is a complementary solution. So let's first find complementary solution. So recall, what is a complementary solution? Complementary solution is a solution to, that is solution to y double prime plus y equals to 0. So what is the characteristic equation in this case? Characteristic equation is r square plus 1 equals to 0. So this gives us r equals to plus or minus I. In that case, you remember it's going to be lambda equals to 0 and mu equals to 1. Yeah, what are the story of lambda and mu? Recall r was lambda plus or minus mu I. And in that case, the two fundamental set of solutions were given by cosine t and sine t. These are fundamental set of solution. We have already proved this. And any linear combination of this gives you the general complementary solution. So this is your complementary solution. Next step. Now we need to find out the particular solution, right? So now to find the particular solution, we are going to do variation of parameters. Again, I want to basically add a point. Note, we cannot use method of undetermined coefficients. If we could, then we'll use that first, okay? Because that's way computationally easier. And we cannot use when y. What is the justification for this question? So what is the justification for not using a method of undetermined coefficient? Because tan t is neither, because your g of t is tan t here, right? So your tan t is not sum or product. It's neither sum or product of exponential, exponential, my bad, exponential, polynomial, or sine or cosine function. Yeah, that's the only time when it is one of these, that's the only time you can use the method of undetermined coefficient. So method of undetermined coefficient is not there. So now we need to compute this thing, right? So let me write that down. So what do we need to compute? So note that u1, then you have yp equals to u1 y1 plus u2 y2, where your u1 is u1t is going to be integral of y2 s g of s divided by Wronskian of w1 and w2 evaluated at s ds and with a minus sign, and u2t is y1 s g of s divided by Wronskian of y1 and y2 evaluated at s ds, and then of course we are going to put the variable t once the integral is done. So we're going to replace that. So now first step is to compute the Wronskian. So what is the Wronskian? So Wronskian of the fundamental solution y1 and y2 of a t is going to be, so we need to compute these guys first, right? So again we have determinant of, what are the solutions we got? We have y1 is, this is your y1 is cos t and y2 is sine t. So let's compute the Wronskian here. So determinant of, so first one we'll take as cosine t. So cosine t, derivative of cosine is, so is minus sine t. Then sine t, derivative of sine t is cosine t. So if we do this, we get cos squared t minus of minus of plus sine squared t, which is going to be 1. So if you replace t by s, also you'll have 1, it's constant 1. So what do we get? This implies u1t is going to be minus y2, which is what? y2 is sine. So sine s. What is g of s? G of t is tan t, so g of s is going to be tan s divided by Wronskian, which is 1 ds, and then after integral you substitute t. Similarly, what is your u2? u2 of t is going to be again integral of cos t, that is your y1 g, which is tan s upon 1 ds, and then after integral you're substituting t. So let's work this out. So note that Wronskian is non-zero, of course, because these are fundamental. So let's compute first one, u1. So u1t, we'll have to use integration by parts now. So u1t is going to be, first I need to compute sine t, tan t, dt, which is by parts. So u is, let's say, okay, so let u be tan, so we get u equals to tan t, we get dv is sine t dt, then you get du is derivative of that, that is secant squared t dt, and v is going to be minus cosine t. So this implies this is going to be, what is the integral of uv? So u dv is uv minus v du. So u is again tan t. So tan t times v, which is cos t, minus v du, which is again cos t times secant square t dt. Now, so this is going to be tan t cos t. There's a minus sign here, right? So let's use that minus sign. So we get, if we use that minus sign, so this will become, so that minus sign got absorbed here and that minus sign got absorbed here. So we got tan t minus, now cos t times secant t is secant t, sorry, cos t times secant square t, because cos and secant multiply to give you 1, so you get 1 secant t is left out, so secant t dt, that is going to be tan t times cos t. What is integral of secant t? The integral of secant t is ln of secant t plus tan t. So this is your u1. So your u1 is going to be, when you multiply this, you can see that sine over cos times cos will cancel. So you get sine t minus ln of secant t plus tan t. Now, similarly, what is your u2? Your u2 is integral of cos t tan t dt. Now cos, and you can see that cos times sine is going to be sine t dt, which is going to be minus cos t. So therefore your yp is, what is your yp? So your yp is going to be u1 y1 plus u2 y2, which is cos t for u1 you get cos t u1 y1, so you have cos t times y1, which is going to be, y1 is this whole thing, so sine t minus ln of secant t plus tan t plus u2 y2, which is minus cos t, y2 is simply sine t. So you see these two guys will cancel each other off. You are left with the solution. You get, this is going to be minus cosine t, this guy multiplied with this thing here, ln of secant t plus tan t. So this is your yp. So then what is your general solution? So the general solution is of form y equals to yp plus yc, or y, that is going to be, generally it's better to write yc plus yp. So we get c1 cos t plus c2 sine t, that is your yc, and then plus yp, which we got there, minus cos t ln of secant t plus. So this is your solution to the whole differential equation. So note that the method of variation parameter is a very general method. It applies to any second order linear differential equation, provided you know the fundamental set of solution. Yeah. Okay. So there are two bottlenecks really. If I give you a second order differential equation, first one is to find out yc, the complementary solution. In this case, it's easy to find, but suppose you have, instead of constant coefficient, you have p of t and q of t. So you will have to use different method than this to find out them. Then the second process is, once you know that, you can find out u1 and u2 using the previous formula. And sometimes it is more tedious to calculate it in general. Okay, thank you for your attention.